We are not talking about. So inside this also I have CIF, and outside also we have the CIF. That is an indication of perfect mixing. So when you have perfect mixing, you can do this also very easily. You take a beaker of water and then put 1 drop of ink when it is thoroughly stirring. What will happen? Immediately that 1 drop of ink, if it is a blue ink or something, so then the entire thing is dispersed, diluted, and then you get the entire contents, entire beaker of water with only blue color. Or if you don't like blue color, you can go to red color, red drop you put. So instantaneously this red or blue color should be dispersed throughout the reactor or throughout that beaker uniformly, right? Okay. Now you do this experiment when continuously water is entering, you have a beaker, and then at some time you just put 1 drop of ink, a blue ink, and then because of the mixing is perfect, that's what our assumption is, and which we can also achieve, then you have this ink color thoroughly dispersed, diluted throughout that volume. Everywhere you have same color, intensity of the color, and instantaneously you will also see the blue color liquid which is coming out. So to start with, we have water is colorless, and then you added a time t and you are stirring very thoroughly, perfect mixing. Then you put a droplet, and instantaneously, that is what is the meaning of perfect mixing. Instantaneously that is distributing, and instantaneously you can also see at the outlet. So that is why that is without reaction, I told. So with reaction, now when you have Ca0 entering, it is dispersed here, and you get some average concentration CIF depending on the conditions, depending on the concentrations, depending on the conversions, all that you will get one concentration. That is why the profile will be suddenly going down and then maintaining the same concentration throughout. That is what is the meaning of perfect mixing. Whereas if you think about a plug flow reactor, you have this continuously decreasing till it reaches CIF. Whereas it suddenly we are losing all concentration. So that is why this is not very efficient method also for us. So I thought this again I will reiterate why mixed flow is slightly, not slightly, I think more inefficient when compared to the plug flow, because it has to do with the use of concentration in the reactor. In a plug flow reactor, the concentration is used beautifully. That means along the length of the reactor in plug flow, I have a rate here, rate here, rate here, rate here, rate here, rate here, rate here. All these average rates are definitely better than having one rate which is corresponding to CIF. Here also CIF, this is a plug flow, PFR. Here also I have mixed flow, this is also CIF. So these two concentrations are same, but how it is reached here, how it is reaching here in plug flow, it is totally different. This is the one along the length. That is why here when I have the Ca0, it becomes slightly less than Ca0, and then I have rate. So that's why if I calculate the number of rates inside a PFR, we have infinite number of rates. In fact, the meaning of 0 to XA dXA by minus RA is a kind of average, one part of average. So that is why plug flow reactor is much better, because the concentration can be very effectively utilized throughout. But in terms of residence time also I will tell you a little bit later, residence times, that also we can just see. Okay. So now this is, I think for continuity sake, I thought if I explain this here, important thing what you have to remember here is the concentration is suddenly dropping. That means we are losing the potential reaction steps, so many in between, because suddenly Ca0 to the outlet concentration CIF it is reaching, without giving us the benefit of using if Ca0 equal to 10 moles per liter, and next stage in the PFR is 9 moles, 8 moles, 7 moles, 6 moles, all that reaction takes place. But here suddenly 10 moles becomes 2 moles or 1 mole if it is 90% conversion. So that is the one way of inefficiency that is coming into mixed flow reactor. Now let us write the material balance. Okay, already I have written this. This is input, output plus accumulation, plus reaction plus accumulation. This is anyway steady state, so it is 0. This is also steady state balance. Steady state. Okay, good. Again I am balancing moles per time. But here see, what is my control volume? That is called control volume. And when you have the change along the length of the reactor, my control volume is a small element. Here I don't have any change except this end and this end. Because in the entire reactor we have only one concentration, there is no change. One temperature, there is no change. I cannot take a element here and write the material balance because everywhere same Ca, everywhere same T. So I can't write any energy balance or any material balance. So that is the reason why we have to take only input as the input here, which is entering, that is Fa0, and output as FAF, plus reaction as minus Ra, and V. This minus Ra has again moles of A per unit time later, per unit volume per unit time, minute. And now what is the V? My control volume V is the entire reactor, that is capital V, which is liters. So now I have later getting cancelled, and then you get again moles per time, moles per minute, everywhere moles per minute. Because Fa0 is moles per minute, FAF is moles per minute, all that, because this notation I have given in the plug flow reactor. So now I have to now simplify. Accumulation equal to 0. This anyway we removed. So now I have to find out volume of the reactor, and this is the volume of the reactor. This is the volume. So now if I write this one as Fa0 minus FAF equal to minus Ra into V. But as I told you, it is better always to put this equation in terms of conversions. 1, 2, 3. And as I told you again, for flow systems, conversion is defined as XA0, FA0, FAF, or FA in general. If you give a condition FAF, it will be FAF, FA0. Right? Okay, good. So now taking this into account, this equation, and applying here, I have FA0 minus FAF, I am writing here FAF, equal to FA0 XA. In fact, XAF. That is what you have written here, XAF. So now substitute equation 5 in 3, because FA0 minus FAF. So FA0 XA. So if I substitute that, FA0 XAF equal to minus Ra into V. Minus Ra into V. Okay. So now our usual expression for design, normally we write like this. V by FA0 equal to XAF by minus Ra. This is the design expression for, this can be 6, this can be 7. So this is the design expression. Here also you have volume, input, kinetics, and then contacting, the meaning of contacting here is, it is a mixed flow reactor. Already you know that it is a mixed flow reactor. But this design expression can be used to calculate volume if conversion you fix. And these two you should know. And FA0 you already know, because that is the input where you have first started market survey, and some people said that you have to produce 10,000 tons per day. Then you can calculate what is the amount of, how many moles of A you have to send into the reactor to get the 10,000 tons, all that. Process calculation, all that, that's what I told. So that is FA0 you know already. Minus Ra is always obtained from kinetics. This is what I have been repeating. This minus Ra can be simply K into Ca, or it can be a complicated reaction like this, or it can be many complications. So now, if you have to calculate the volume, I should know XAF minus Ra, FA0. So there are 4 volumes, at least 3 you should know before calculating the other one. And for a given reactor, that means someone tells that I have 10 meter cubed reactor, why don't you use that? So already I have V equal to 10 meter cube. FA naught I know 10,000 tons per day I have to produce, right? And then we have a minus area from kinetics I should get. In fact, in chemical reaction engineering, getting rate equation is very difficult when compared to any other thing, right? Okay, good. So that is XAF. XAF you can calculate for a given reactor. So this is what is the design expression for design expression for the mixed flow reactor. So now we have 3 reactors. Let us summarize those 3 reactors, right? Okay. Comparison of reactors, ideal reactors. I would like to write all 3. For batch, it is T by Ca naught equal to 0 to XA dXA by minus RA. And for PFR, this is continuous. Continuous. For PFR, it is V by FA naught equal to 0 to XA dXA by minus RA. And for MFR, it is V by FA naught equal to XA or XAF by minus RA. These are the 3 equations what we have. That's all. Entire chemical reaction engineering, most of the time we try to use ideal reactors. Only problem with ideal reactors is plug flow, because it is not easy to maintain plug flow, and otherwise all other 2 reactors, ideal rate expression, ideal design expression itself can be used to find out what is the volume of the reactor for a given conversion. That's all. Okay, good. So now when I plot, you would have seen that this one and this one is exactly same. For batch reactor and plug flow reactor, the right hand side is exactly same. That means there must be something similarly going on in a batch reactor and plug flow reactor. What is that? That is, in a batch reactor also each and every particle is spending exactly the same time in a batch reactor. Why? Because you are now putting the reactants and then closing, and after closing that you wait for 10 minutes. So that means each and every particle is also exactly spending the same time. So now what you have here is that when I have this integral same, the similarity between plug flow reactor and batch reactor is that the particles are going to spend exactly the same time. Okay. So here we have the same thing. That is, so the assumption here in batch reactor also exactly same as plug flow reactor, because the particles are going to spend exactly the same time. In a batch reactor, because you don't have a flow will not come into picture here in a batch reactor. That's why it is time by concentration, and I also told you how this time can be converted in terms of the total volume and all that in the last class. Good. Okay. So now when I compare these two, I will plot these two, the continuous systems. So I have minus 1 by RA equal to, I think I have not plotted this. Okay, good. So this is XA. Let me first plot. I think this already you have plotted the plug flow reactor. Let us plot now mixed flow reactor first. The relationship between 1 by minus RA versus XA is same. It is something like this. Again, as I told you, idea is as conversion is increasing, rate decreases. When rate is decreasing, this 1 by minus RA increases. So that's why it is increasing like this. And when you are going to almost 100% conversion, it goes to infinity. Good. That is the simple thing. But now this expression is nothing but an algebraic expression, right? 1 by minus RA. This actually is nothing but y equal to mx. So if I take this x, this is y, yx. 1 by minus RA I will take as y, and y into x. Y into x is nothing but I have x somewhere here, which may be XAF here, and then I have 1 by minus RA somewhere here. It depends on how much conversion you take. So now this is a rectangle area because this is 1 by minus RA as Y and Y into XA. So Y XA. So that's why this total area under the curve will be V by F A naught. So naturally this entire area is larger than this area because this area is for PFR. This is for PFR. And this one is for MFR. And how much extra area you have? This extra area is this much extra you have to spend for mixture flow reactor. Why? I have told you already the reason. Because here you have a problem with the mixture flow reactor where you are not able to utilize the concentration very effectively. We can also tell this in terms of residence time distributions. Residence time distributions, RTD we call. Residence time distribution, RTD. Do this experiment again. Let me take an MFR. MFR means a beaker of water, and then I have stirring. Water I am continuously pouring. Water is coming out. This is water. Water also coming out. So I have volume V, and I also have volumetric flow rate and all that, no problem. So many liters per minute is entering there. So now at time t equal to 0, I am just now putting a drop of ink, a drop of tracer we call, one drop is put at time t equal to 0. So when this drop is just entered, because of perfect mixing, that is thoroughly distributed. And instantaneously, I will also see that color. There is no reaction. Please remember, I am not talking about reaction. To give the idea of resistance time distribution, I am conducting an experiment, mental experiment with ink, water and a beaker where I can see, because it is a glass beaker, so I can see clearly what is happening there. So then at time t equal to 0, I added some kind of blue color ink that is thoroughly distributed, and instantaneously here, the moment I added, I will also see this concentration, some concentration of blue color here, right? Okay, one drop. So now what happens to the one drop? The moment it touches, it is totally torn into part and then distributed throughout the reactor or throughout the beaker. So now I have some diluted ink concentration. If I plot that, I will have C, that is at time t equal to 0. I can also calculate. If I put now 10 grams of ink at time t equal to 0, let us imagine, I think one drop is 10, this is a large imagination, but I am just giving you a number which you can easily remember. 10 grams I added at time t equal to 0. If the volume is 1 liter, the concentration will be instantaneously 10 grams per liter. If it is a 1 liter beaker. So that is the starting point for a C naught. From then onwards, we can show mathematically also this exponentially decreases. And then it goes to infinite time to remove all the color from that, because you see that we added only one drop. Water is continuously entering. Water is water. There is no color at all. And here you have colored water. Finally, this colored water to become pure water, the original water, it takes almost infinite time. I think we can write material balance and then do it, and that comes in residence time distribution. But my point here is, we have the water molecules coming, ink molecules coming from time t equal to 0 to infinity. This is what is the RTD of MFR, residence time distribution. So that means the molecules residence time is distributed from 0 to infinity. That is the meaning. So that is why the molecules, and immediately also some molecules are coming. After some time some more molecules are coming, after some time some more molecules are coming, after some time some more molecules are coming. So if you extend this to reaction, the reaction here will be very, very small or zero sometimes, because immediately the molecule entered, came out. Immediately a packet of molecules entered, came out. Where is the reaction? There is no reaction. That is why we are losing a lot of concentration, and then you will get, to compensate that, you have to use a large volume when compared to your plug flow reactor. Now let us see. Let us do the same experiment for PFR. So in PFR I have this kind of equipment. Again I have water. I took a small glass tube and very high velocity so that I can maintain plug flow. It is perfect plug flow there, perfect plug flow, ideal assumption. Then at time t equal to 0, again I have put that droplet, but the droplet now is made as a disk. You have seen computer disks. So now imagine that the droplet made as a thin slice of disk which has the same diameter as the pipe. It just entered. So that is, let us say, blue color. I don't have blue color, but anyway I will use red color. Yeah, that is what it enters. So now, because by definition axial mixing equal to 0, radial mixing equal to infinity, and then each and every particle should spend exactly same time, because of all these conditions it will automatically do that. So now when I look at this disk, it is not disturbed at all. I can see here at 1/4 of the time, half of the time I can see here, 3/4 of the time, and finally it comes, the disk comes as it is. Now you see what is the residence time distribution of these red molecules. Like here what you have done, ink molecules, these are the ink color, right? Here also red color is without any disturbance moving like this, like this, like this, like this, and finally exciting here with same residence time, whatever the entire residence time. So now each and every particle in this disk is spending exactly the same time. So now conversion in each and every particles of this disk is same, and then the average of is exactly same, and we are not losing any molecules earlier coming or late coming and all that. That is why you get the maximum conversion in plug flow reactor. That is the meaning of this graph. I don't know how much you could catch, but I think you need some thinking about this. Why a plug flow reactor is better than a mixed flow reactor? Because it is due to residence time distribution. The residence time distribution in PFR, here RTD in MFR 0 to infinity, and in plug flow RTD equal to 0. There is no distribution of residence time, because each and every particle spending exactly same time. Each and every particle spending exactly same time. So that is the reason why you get more conversion in a plug flow reactor than the mixed flow reactor. Good. I think I could tell sufficient reasons why a plug flow reactor is better than a mixed flow reactor. But all this discussion is only valid for n greater than 0 orders, order of reactions. Okay, all positive order reactions, all this discussion. For negative order, it is something nice which you can think of. I don't want to give that. Okay, good. So now, yeah, someone was also asking me in the last class that what is the advantage of ideality, because I think you are saying that the ideality concept is not valid for plug flow. I will just give you one example. If I have, okay, so now let me write an equation for conversion if I have an ideal PFR. We only have problem with the ideality in PFR because we maintain that so easily. So I think we will discuss only that. By assuming ideal plug flow, if I have A going to R, first order reaction where minus RA equal to K into Ca, 1 mole, there is no volume change and all that. So this kind of reaction I have. I have the design expression for ideal plug flow as V by Fa naught equal to 0 to Xa dxa by minus RA, where this minus RA is nothing but first order reaction. 0 to xa dxa minus RA can be written into K into Ca naught, K into Ca. That K into Ca naught can also be written as Ca naught into 1 minus xa. Why? Because finally my integration variable is x, conversion. So I have to convert this into xa. And how I got this equation is, I have xa definition for constant systems is Ca naught minus Ca by Ca naught. I have used that here. Ca equal to 1 minus xa. So now K, and because isothermal reaction, K is constant and Ca naught is constant, you bring it out. This is equal to K Ca naught. Integral 0 to xa dxa by minus RA. Sorry, 1 minus xa. So when I integrate this, what I get here is, this is equal to minus ln 1 minus xa divided by K into Ca naught. This is V by Fa naught. V by Fa naught. V by Fa naught equal to minus ln 1 minus xa K Ca naught. So then if I want to calculate either conversion or volume, I can convert. So now I will write this one as minus ln 1 minus xa equal to V K Ca naught by Fa naught. Correct? No? Yeah. Good. So 1 minus xa equal to e power minus all this. Okay, I think let me write. Let me write anyway instead of shortcut. 1 minus xa equal to e power minus V K Ca naught by Fa naught. So this is the one. If you know V for a given reaction, you know K kinetics, you know Ca naught input, Fa naught input, initial concentration and initial flow rate. So you can calculate xa. This is for first order reaction. Now, if I don't take ideal reactor, non-ideal reactor, non-ideal PFR, same reaction A going to R with the same rate expression, K equal to, no, minus RA equal to K into Ca. I will give you the final solution. I don't want to give all the differential equations, so for lack of time. So now the same with non-ideality, and that non-ideality is only axial mixing. Only one non-ideality I have taken. There is axial mixing. So that means all the molecules are not spending exactly same time. Some molecules are coming forward and some molecules are coming backward because of mixing. I gave you this example of Q, which is moving forward and backward, and then you can find out, you know, what is the mixing zone and all that. I think there are techniques to be found. But my interest is to show you what is the beauty in assuming the ideality. So now with the axial mixing as non-ideality, non-ideal PFR with the axial mixing, okay. With the axial mixing alone, I will write this expression, please take it. 1 minus xa equal to 4a exponential half ul by d whole thing divided by 1 plus a whole square exponential a by 2 ul by d minus 1 minus a whole square exponential minus a by 2 ul by d. This is the equation, again not over. It is where a equal to, because a we have not defined what is that, it is square root of 1 plus k tau d by UL, where again tau equal to volume by volumetric flow rate, etc. And where U is the velocity. U is velocity and L is length of the reactor. L is length of the reactor, and D equal to diffusivity, because we are talking about axial diffusion. So axial diffusion, axial mixing, axial diffusion is characterized by a diffusivity coefficient which you know as Fick's law diffusivity, DAB, right? So that kind of diffusivity what you have. So this is the equation what you get for same first order reaction. If I don't assume ideality and I take only one axial mixing as the non-ideality, there are other non-idealities like channeling, there are other non-idealities like radial mixing also not correct. So if you have axial mixing as non-ideality, radial mixing as non-ideality, and also channeling as non-ideality, dead space as non-ideality, then I have to write the equation covering the whole board. So that is the beauty in having, you see, this is the expression for first order reaction, assuming ideal, and this is the equation we have to use to calculate conversions for a given volume, or otherwise to calculate length of the reactor or volume of the reactor for given conversion. For a given conversion you have to use either this or this depending on your assumption. That's why I think last time, I think maybe TKM college only asked someone, sir, then why are you doing non-ideality? This is the reason why we are not doing non-ideality and we are assuming only ideality. And fairly one can, depending on the gas phase reactions, one can also closely approximate towards plug flow, even though there is no ideal plug flow anywhere. So this is what is that I would like to tell the difference between ideal conditions and non-ideal conditions. Okay. So now the next one, see, we have V by FA naught equal to 0 to XA dXA by minus RA for PFR. For MFR, we also have FA naught 0 to XA dXA by minus RA. Oh, sorry. For MFR, XA by minus RA. However, we can also write these equations in terms of tau. Tau means the mean residence time, space time. Space time tau, which is defined as, in terms of equations, volume by volumetric flow rate. Volume by volumetric flow rate at known at specified conditions. At specified conditions. The meaning of these specified conditions is that because volumetric flow rate changes with temperature and pressure and all that, and that's why one should know that at what point in the reactor this volumetric flow rate is valid. So most of the time we take at the entry. So this may be V naught. So this is volume of the reactor, this is V naught, here it may be different. So now this is the volumetric flow rate, V naught is the volumetric flow rate. Volumetric flow rate. The units of this will be, this is liters and this will be liter per minute. Volumetric flow rate V is liter per minute or meter cubed per minute or meter cubed per hour, whatever. So now later will get cancelled, you get the minute. Of course, it's not the simple thing I am deriving here, but through residence time distribution studies also we can prove the space time volume by volumetric flow rate as the space time. And space time, physical meaning of space time is, it tells us that what is the time required for processing one volume of one reactor volume. One reactor volume to process, what is the time required. So that is the meaning of space time. So I think you can get more information from your teachers about this. I don't have much time, I think we better move for one more thing and then discussion. Discussion is much more important for us. So space time, and there is another term called holding time. I am just mentioning this, you can kindly ask your teachers. Holding time or mean residence time. Yeah, mean residence time. But my request is kindly ask your teachers what is the meaning and what is the connection between space time and mean residence time. Personally, as Krishnaya, if you ask me, I don't care about space time. The reason is, this is the design expression for plug flow reactor. This is the design expression for mixed flow reactor. Where is the time coming for me? Where is the time coming? And my job is to find out volume of the reactor if conversion is given. Even here, volume of reactor if conversion is given. Why do I need time? So that is why my recommendation is don't bother about this. But sometimes we talk about that. The reason is that we have batch reactor expression T by CA naught equal to 0 to, this is what is spoiling us. This is batch reactor. Because you first learnt batch reactor in your high school and also 12th class or so, which is now derived as time by CA naught. So that is why we would like to write these two equations also in terms of tau by CA naught. So writing that in terms of tau by CA naught, I think I'll write that. Yeah. So for MFR and all that, this is tau by V naught, so V naught, and this is also tau by CA naught. Tau by CA naught, this is also tau by CA naught. So just to have some kind of similarity with the batch reactor, unnecessarily we are bringing this complication with us, but I don't require space time for the design of the reactor. So that's why I always put a question mark here. If you like it, take it. Otherwise, these are the equations which are more than enough. Yeah. So these are the equations which is more than enough for you. But for batch reactor, you don't have any choice. You have to use this. There is no choice at all. Because that is the automatically through fundamental principles like writing the material balance and all that, you will get only that expression. Whereas for continuous reactors, you get, this is the natural performance equation. This is the natural variables that automatically come. This is artificially we are creating to compare this and this, which is waste of time for us. So that's why I never liked that. So anyway, you discuss with your teachers and then you try to find out. If you are comfortable, you can definitely use that. Okay. So now let us take one example. I think example to calculate PFR and MFR volumes. Okay, so that is the one. You can just read. I think, I hope you can, all of you can read that. A homogeneous isothermal liquid phase reaction, you see how many conditions are given. A homogeneous reaction which is isothermal, which is also liquid. So all these conditions, that gives some information for you. So when homogeneous means the physical conditions like mass transfer and heat transfer not coming. Isothermal means temperature throughout the reactor same. So that means I have Arrhenius equation, but it is only valid at one temperature. That means K value is easy for me to get. It is a liquid phase reaction, meaning that it is not gas phase where volume changes. Liquid phase reactions are maintaining the same density throughout the reaction, and it is A going to R. Good. That is the first order reaction, simply. Right? Oh, we are not given that. Yeah. Okay. So the rate constant at the operating temperature is 0.1 minutes inverse. This K value, when in homogeneous systems, if someone gives you K value as time inverse, that indicates it is the order of reaction, and that order of reaction here is first order, even though we have not mentioned. But because it is a first time you are exposed to this kind of problems, I should have given it is a first order reaction. But anyway, indirectly, you also in the examinations we cheat you many times. We will give only this 0.1 minutes inverse. Then you have to find out if it is homogeneous reaction, whether it is first order, or depending on the units you can find out for homogeneous reaction, right? Okay. So the flow rate, yeah, the rate constant is K, which is 0.1 minutes inverse. Let me write the data. The flow rate of pure reactant stream is 10 moles per minute. 10 moles per minute. That means it is molar flow rate, which we are indicating as FA0. This is 10 moles per minute. Good. That is FA0. And with a concentration, inlet concentration as Ca0, which is nothing but 1 mole per liter. Yeah. We have to find out what is the volume of plug flow reactor and mixed flow reactor for a conversion of 90%. 0.9 is the conversion. Now, how do we calculate the volumes? First, let us do it for plug flow. You know that for plug flow, the design expression is, this is ideal reactors what we are talking. V by Fa0 equal to 0 to Xa dxa by minus Ra, where this is a first order reaction, constant density, all that gives me, this is nothing but 0 to Xa dxa by K Ca0 into 1 minus Xa. Just some time back, I have given a final solution for this because K and C0 is constant. So I don't have to integrate. This is K into C0. So the integrate, if I take this, the integration of this will be minus ln 1 minus Xa with the limits and all that. Oh, sorry. Yeah. So this is the expression. What is that we have to calculate? The volume of plug flow reactor. So V plug flow reactor is Fa0 K into Ca0 minus ln 1 minus Xa. Yeah. Now let us substitute these values. Fa0 I know. Fa0 is 10 moles per. Fa0 is 10 moles per minute. And K is 0.1 minutes inverse. So per minute. And Ca0 is 1 mole per liter. So this is 1 mole per liter. So now, okay. This is minus ln Xa equal to 0.9. So this will be 0.1. So when I substitute, okay, let me also cancel out. Minute will get cancelled. Moles. This is a good practice. When you write the units and then strike off whatever common things are there, and then you will end up only with the letters here. So you don't make any dimensional mistake if you write all the units when you are solving the problem. So now I have 10 divided by 0.1 and divided by 1, this is 100. Multiplied by, you have this minus 0.1 is nothing but 2.0, no? Yeah, 2.30, yeah, 2.303 or something. I will take approximate as 2.3 because minus is there, minus will get cancelled, this is 1. So now you have here 230 liters. Hmm. 230 liters of VPFR. That is the one. Good. So now I think this is very easy for you to calculate. Straightforward. Now let me do it for, I will leave this one as it is. Now let me do it for mixed flow reactor, MFR. Same data for mixed flow reactor. But now what is the design expression for mixed flow reactor, MFR? Just now we have derived that is V by Fa0 equal to Xa by minus Ra. Again, minus Ra with all these conditions is nothing but Xa K Ca0 1 minus Xa. What is that I have to calculate? V. So V can be written as Fa0. I am taking this Fa0 here. Yeah, Fa0 Xa K Ca0 1 minus Xa. If I substitute all the values, Fa0 is again 10 moles per minute. Xa no unit, so this is 0.9. And K value is 0.1 minutes inverse, so per minute. Ca naught is 1 mole per liter, and 1 minus Xa equal to 1 minus 0.9, it is 0.1. There are no units. Again let us cancel. Minute gets cancelled, mole gets cancelled, so everything you get only in terms of liters. Now we see this is 10.9, so this is 9 divided by 0.1, so that is 90 divided by 0.1, so 900. So the volume is 900 liters. So VPFR is this, VMFR equal to 900 liters. Good. So 230 liters for the same 90% conversion. If I am conducting this reaction in a plug flow reactor, I get 230 liters volume. Whereas if I use mixed flow reactor, I am getting 900 liters of volume. Don't be happy that 900 is large, I will take it. Right? So 900 is bad, because in a chemical industry, you should have the equipment as small as possible, but not as large as possible. Only thing you want as large as possible is the money. But here, you have to now design the reactor where it should be as small as possible. Right? Okay. So that is and the reasons also I gave you why you get plug flow reactor, because in a plug flow reactor, each and every particle is spending exactly same. All those particles will get converted to 90% conversion. Whereas in a mixed flow reactor, because of the residence time distribution, some particles will come very quickly out of the reactor. So that means the conversion in that reactor is almost zero. And there are particles which are coming till infinity, already converted but slowly coming out like lazy fellow. So the average of that is definitely very small conversion to compensate, because conversion is fixed. Conversion is fixed. So to make these particles react more time, you should provide more volume. When you provide more volume, then most of the particles may stay and then give this kind of conversion. This kind of conversion. So that is why for a given conversion, always mixed flow is larger volume when compared to the plug flow if the orders are n greater than 0. If the orders are n greater than 0. So that is very important for us. So this is the problem I just want to tell you, so that I can support with calculations whatever I told, saying that we have plug flow more efficient than mixed flow because of simply the assumption of each and every particle spending exactly the same time. That is the one. So I think I have covered whatever I wanted to do in the 6 hours, and I should have told so many times about so many things normally if I have more and more time, but this is just enough for you to understand. Absolutely, I don't think you have missed anything as far as I know. So that's why kindly try to understand this, and kindly try to send me the mails if you have not understood something. And I opened the forum where I think I found no questions at all from students. I think yeah. Yeah. Now I think anyway I am ready for answering questions, and let us start discussion, so that if you have any doubts, you can always question me, and then we will try to answer that. Okay. If there are any questions, kindly ask. BSAR, I think it is a good question, because it is, you are talking about ideal condition can be used for modeling and simulation. Definitely non-ideal conditions are so difficult. No one will try to use non-ideal conditions and try to simulate. So that is why most of the time for simulation, you take the ideal conditions and then try to model and then simulate, because your model should be based on ideal conditions, and naturally you are simulating between a range of variables. So that's why ideal condition is always used for, I mean, many times is used for modeling and simulation. Yes. The answer is yes. Yeah. Sir, is tracer the only method to find the residence time? No, not the tracer method gives you residence time distribution. The tracer method gives you residence time distribution, and from residence time distribution you can calculate what is the mean residence time in that reactor, right? I don't know whether you have been exposed to mean residence time, I'm sorry, residence time distribution. Yeah, once more I will repeat. Yeah, I think kindly listen, all the colleges also can listen to these questions, because all these questions are very good questions. You also will have the similar kinds of doubts. The question is, yeah, probably all of you may be seeing this. The question is tracer method, is tracer is the only method to find out residence time? From tracer method, what you find is the residence time distribution. We will find out the tracer concentration, how it is varying with time, and then try to find out the distribution. By plotting you will know, and using that information by finding out the mean, the first moment mean, you can find out the residence time in the reactor. Okay, good. I think that is nice. Oh, okay. I think I'm sorry, there is no connection between rate equation or step input or pulse input. Normally step input or pulse input are used to find out this residence time distribution. Reaction is not coming there. The normal way what we do, right? The complicated way one can do also, the actual reactions also can be used to find out residence time distribution, which is very complicated method, and no one generally uses that method. So there is no connection between step input or pulse input and rate equation, as far as I know, right? So the reason is step input or pulse input, again I am repeating, it is used for finding out tracer experiments, using tracer experiment to find out the non-idealities and residence time distribution, etc. Residence time distribution automatically gives non-idealities. So no connection between rate equation or step input or pulse input. So please, BSAR, does space time and holding time have influence on batch reactor? Yeah, I think it is straightforward. Answer is batch reactor, where is the flow? Where is the mean residence time? The mean residence time you are already fixing, because you are not allowing the molecules to get out. At time t equal to 0, you put everything and close all the doors and wait for 10 minutes. Right? So the mean residence time or holding time, space time and holding time refers to continuous systems. And batch system is batch reaction time, which you are able to calculate from the design expression which we have derived earlier. That's why when you are talking space time, I never mentioned anything about batch reactor, except that because of the similar equation T by C A naught, we would like to convert the other two reactors also as tau by C A naught, which is space time, which is unnecessary. That's why I think last maybe 10 years or so in IIT Madras, when I teach reaction engineering, I tell them that don't worry about tau at all. It is not coming in the design. If you see the design expressions, except in batch reactor, the time comes. The other reactors, there is no time coming, and directly the volume comes. And what we are interested in is in volume, not with time. By the way, how do you design if I give you tau? Tau only. If you don't know volume by volumetric flow rate equal to tau. So that is why space time and holding time they are not connected with batch reactor. It is only defined for continuous reactors. Okay? Thank you. Yes,
sir. Sir, we would like to know, is it possible for a isothermal condition, can we derive a what is the expression for non-isothermal condition?
Yeah.
Is it possible to derive an expression isothermal condition?
Yeah. See, I will tell you. I will give you. I think that is a good question, because I mean, it's not my portion of doing that. That's why I have not done non-isothermal. Someone may be doing it for you. I will tell you in a very simple manner why we need for non-isothermal energy balance. See, you know that we have V by FA naught. I am taking example as PFR. If it is a first order reaction, I have minus RA, and for first order I am taking K into CA. If it is non-isothermal, then this K has to be written as dxa by this K is Arrhenius equation. Please remember, Arrhenius equation is nothing but K naught, that is frequency factor, minus E by RT into CA, and the CA can be written as CA naught into 1 minus XA. All this you know except this extra information. But now you see, under this integral we have a temperature T, which is also a variable. Temperature is changing and conversion is changing. Both are changing in this. K naught is constant, CA naught is constant, E by R is constant, right? E by R is constant, K naught is constant, CA naught is constant. So what you have is only temperature and conversion. So that is why you have to express T as a function of XA. Otherwise, I can't integrate, because the variable of integration here is only XA. But I have another variable that is coming into the equation under integration, which is T. So unless I convert this entire expression into T or into X, I can't integrate. So that is why you need information connecting temperature with conversion. So this information you get from energy balance. So for isothermal, this is not required because this is constant K, which I can take out. I don't it won't come into the integration. But now if it is non-isothermal, temperature is changing inside the reactor when the things are moving. If it is a plug flow reactor along the length. So now that information I have to get, how temperature is changing with conversion, the relationship between temperature and conversion. So that is the reason why I need an extra equation, that is energy balance equation, which connects me temperature and conversion. Now that temperature and conversion I can substitute here. I will also give you one of the simple relationships for adiabatic system also. This is T equal to T naught initial temperature into some beta. It is a constant which you have to find out thermodynamic properties. This is the one, what is one of the energy balance equations. This relationship you get from the energy balance, which is for adiabatic system. You see now, this is the relationship between temperature and conversion. Good. And now this equation I will substitute here. When I put this T equal to T naught and beta, beta is constant, T naught is constant. It is only a variable in XA. So now this entire equation will be only under XA. Now I can integrate. So that is the reason why for non-isothermal reactions you need another extra equation from energy balance, and that gives only the relationship between temperature and conversion. Right? Have you understood?
Yes, no. Sir. Thank you.
Yeah. In general, which reactor is more advantage? Yeah, I think I told you this. For always for n greater than 0 reactions, plug flow is the best. Why? Because each and every particle is spending exactly the same time. You are supposed to get more conversion in that. But there are questions now. If the reaction is very slow, you have to provide very large residence time, where the reactor length can be from Earth to Moon. It can be so long if the reaction is very, very slow. That's why now as engineers, you have to find out, okay, I don't want to send my plug flow reactor from the surface of the Earth to the Moon so long. So that is why now can I go to some other system where I can manage on Earth itself, right? So if you want to produce very large residence times, naturally we will try to go for tank reactors. So the tank reactors are batch and mixed flow, and we clearly know batch reactors are most of the time used for small scale production. And if it is a continuous reactor and large scale production, large residence time required, then you need mixed flow reactors. So that is why, even though theoretically for n greater than 0 orders, plug flow reactor is better, but we are not able to use plug flow in all situations. So that is why we cannot say, but theoretically it is plug flow which is better for n greater than 0 order. Okay? Yeah, what are the other equations? Other questions? Sridhar sir. Okay. Sir, for variable volume system, which reactor can be used to get better efficiency? Okay. For variable also, plug flow is the better, provided it satisfies all other conditions like small residence times and all that, right? Either for variable or constant, all the particles will spend exactly the same time. So that's why plug flow is the better for n greater than 0 all the time. So that's not a problem at all for you if you want to use plug flow and then see its limitations. Okay, I think some more. Is there any direct relation between PFR and MFR? Okay, is there any direct relationship between PFR and MFR? What do you mean by direct relationship for? Okay, PFR is one kind of reactor and MFR is another kind of reactor, right? You can only compare them whether which one is better. That is the relationship what we have. So I don't know what is the direct relationship. Direct or indirect, we can only try to compare their volumes for a given conversion or conversion for a given volume. It is only comparison, which one is better and which one is not better, right? Other than that, I think direct relationship, no, I think it's only comparison what you can make. Okay, anything else? Oh yeah, there is another GCT. Yeah, yes, very good. I think there is another reactor, this ideal, 3 ideal basic reactors what we have done here. There is a reactor called recycle reactor. So if you take the product stream at the end of the reactor and send it back to the inlet, and depending on how much product you are sending back for the reactor to the reactor inlet, that's called recycle ratio. Depending on that, we can also try to use that reactor for some special conditions, particularly for multiple reactions. Many people think that by taking the recirculation back, you will increase conversion. No, you can't increase. That one reactor itself can give you, depending on recycle ratio, if recycle ratio equal to 0, you will have ideal plug flow, which is the highest, highest efficiency, which has got highest efficiency. And if you take infinite recycle ratio, that means all the product again sent it back, then you have mixed flow condition. So the advantage of using recirculating the recycle reactor is to get the advantage of what is called mixing. Okay, I think this concept also probably is good for you. For PFR, mixing equal to 0, because we are not allowing radial mixing and all that, sorry, axial mixing and all that. And whereas for a mixed flow reactor, mixing equal to infinity. So in between, if you want to have some kind of mixing, recycle reactor is the best one. And efficiency wise, plug flow is the best one, right? And the question answer to that is, we can recirculate the fluid, but why? Why do you want to do that? You should definitely know why are you now trying to recirculate fluids in the PFR. That's all. If you know that, recirculation can be used for plug flow reactor. Okay, good. Yeah. Is there performance equation for fed batch same that of performance equation for fed batch same that of MFR? Okay, both cannot be same. I think the operation itself is different, right? We are talking about mixed flow reactor which we derived. We are talking about fed batch reactor where we have not derived. If there are two reactants, one reactant can be taken in the reactor itself. Let me draw that. Okay. So now you take one reactor and I have two reactants to make it as fed batch. You take the reactant A here. This is A. I don't know whether they can see. Yeah. This is A, already fed. And now slowly you add B, maybe drop by drop. Right? This is semi-continuous or fed batch. Right? This is batch and now you are again feeding with some other thing. This analysis is totally different. So you cannot have mixed flow reactor as that of fed batch. So actually this is more complicated because when you are adding B, slowly the level is increasing, and when slowly the level is increasing, along with that reaction also going on. So you have to take volume change into account, reaction rates into account with the time. So that is why it is mathematically slightly more complicated than the equations what we have derived. But the procedure is again writing input, that universal equation what I have written for batch reactor, mixed flow reactor, plug flow reactor. The procedure is exactly same. But one extra equation also you get here because the volume is increasing slowly when you are adding drop by drop. So that if you take into account, then you can solve that. But answer is mixed flow reactor is different and fed batch reactor is different. You cannot have same equation. Okay? Yeah. Next one. Yeah, one more question. GCT again. In MFR, whether steady state or unsteady state is maintained. Yeah, I told you in the beginning itself that these two reactors what we have derived is steady state, isothermal and also homogeneous. These are the conditions. Steady state reactors, isothermal reactors and homogeneous reactors. That means only one phase is entering and then one phase is coming out. Right? Yeah, everyone is satisfied or everyone is unsatisfied? Okay, anyway, so thanks. I think almost as per registration there are supposed to be around 800 students, and out of that I think if all of you get benefited I will be very happy. But I think if you have doubts you can always send email to me, and my email I think I can straight away answer if I have yeah. So my email address is krishnak@iatm.ac.in. Yeah. So that is my email address. Straight away it comes to me. I don't have to go to again this QEEE pack and all that. So if you have really doubts, I will be happy to answer to you, and then in that process I will also learn something. So that's why use this email krishnak@iatm.ac.in if you have some doubts. I hope you enjoyed, but definitely I have enjoyed what I was teaching. Okay, if there are no questions, all the best to you, but you have to ask your faculty members if you have not understood something, how to connect what I told and what they are going to do in the rest of the course. And I also request all the teachers, if they have any, I am sure most of you understand, most of you can explain very well, but if you need any information from me for discussion or also to make something clear to your students, I will be always available. You can use this email, personal email, and then I will be happy to interact with you. I am now requesting all the faculty members who are sitting in that classes. If you need any information, definitely I will be very happy, because after all the entire exercise is QEEE is to have a good course in the whatever courses we give, right? So to fulfill that, definitely I will be happy to spend more time, and in that process I may also learn something. So that's why please interact with me, all the teachers, if you need something. Okay, thank you.